Hi guys, welcome back. So in this video we're going to talk about structures, signatures, and also we're going to talk about functors, applicatives, and monads. So, what are structures? Well, we have actually been working with the structures for a few episodes now. You guys just might not know it. So all of these things, text slash monoid, int slash number, int slash show, these are all structures. So what is a structure? Well, before we talk about structures, first we need to talk about signatures. But first I'm going to talk about the names. Where do those names come from? They might be weird, to you guys, because you guys might be more familiar with classes from object-oriented programming, and some of you guys who might know something about structures might know it from C or other low-level languages. And the structures in a way resemble that, but not exactly, not completely at least. And also, some of you guys who might be more familiar with Haskell, for instance, might know of type classes. Now, structures and signatures, the terms come from the ML family of languages. So, standard ML, OCaml, F#. From the ML family of languages comes this concept of a signature. So we have already seen how to define types, right? So we have something like type of lists, which looks like this. Oops, forgot the type. Here, there you go. We have also seen something like, if I recall correctly, we have seen the types of records like user, pretty simple. Well, let's say that signatures are also types in some way. They're types, but they're types whose members are meant to be used not just as containers of data, like in the case of our user type here, but more like containers of functionality. Or rather, signatures are specifications for such containers of functionality. So let's see something like that. Let's talk about this number signature. So I'm gonna show you a nice. Let's see the definition of number. Wait, maybe not. It's a little bit too advanced for you guys right now. What can I show you? See, I want to show you something that contains more than one element, but not too many, because the ones that contain too many tend to have a little bit of extra magic in them. Okay, so it looks. Wait, still too much magic. Not for you guys right now. You know what? I'm gonna go with the simplest one. Equality. So this is an actual signature that you can find in Lux, in the standard library. So there is the Lux/control/ec or ec module. It contains the ec or ec. I don't know which will be the proper way of pronouncing it, but it contains the equality, signature, which basically just contains one member, which is this one, which is in this case a function. So how does this work? This syntax is different from the def type syntax that we have seen. Well, equality is a signature that contains one type variable, which is a. We didn't have to put the all macro for adding type variables, because it's kind of like when we do the list type. This utilizes a for all, or this utilizes a all macro behind the scenes, but you can write it this way to avoid typing extra stuff, so it's easier. The same way goes for this. So we have this one type variable and we have this one member. Members in signature are specified in this way. We have this column here, which stands for type annotation. we have a type, and then we have the name of the member, which in this case is just an equals sign. Because this is an equality signature, we want to have equality functions associated with our equality signature. And this is a function such that if you give me two elements of type A, which we instantiate here, I'm gonna give you a boolean. So you can make equality for numbers, in which case A will be the int type or the real type, for instance. You can make equality for text, and there are equality implementations for many types already in the standard library, which you can use without having to implement them yourselves. Plus, you can write your own implementations for your own custom data types. So we have that. So basically, this ultimately, just the sugars, because signatures are actually not primitives in looks. They're actually implemented in terms of just regular types. So this will actually transform into something like this: def type ig a. Then we have this here, and this is what this will transform into: just a record type that contains one element, which is the equality element, which has this type. Simple as that. And we can have signatures with much more elements. In the same way you can have record types with many elements. Just the same. But I wanted to show you a few ones that had more elements, but it's a little bit harder because the ones that have more elements in the standard library tend to have so many elements that I do some tricks to avoid typing too much. And right now we are not there yet at the point in which we can discuss those tricks because they're a little bit more advanced. But we're gonna see them in later videos. But maybe I can show you the fold one. Oh, here I can show you that this is a fold signature. I'm not gonna talk too much about what it does right now, but here you can see that it has two members, fold L and fold R. And the fold signature itself introduces one type variable, which is F, but fold L requires both fold L and fold R require two more type variables, which are independent of just a signature. And that is why I use universal quantification to introduce them in themselves, so they can refer to the one defined on the fold, and they can also refer to their own extra type variables. And again, I'm not going to talk too much about what folds are here, but suffice to say that you can have as many elements in your signature as you want. Now, I mentioned here that signatures are like specifications for things, and you can consider that it's like a type is a specification for values. It's the same way. You cannot use the signature itself to check equality between things because there is no code, but you can use it to make sure that a particular implementation does match the expectations of an equality data type. So what would fit those specifications? Well, the opposite, or the complementary thing to signatures, are called structures. And a structure is to a signature as a value is to a type. The value is described by the type, but it is an actual thing that you can use, like a number. We can talk about number types, but number types are useless if you want to add things. What you need are actual numbers. You cannot add the int type to itself, but you can add 5 to 3 to get 8. Pretty simple. In the same way, you cannot use signatures, but you can use structures, because structures actually implement the signatures, and the structures are actually values. So let's see an actual implementation of equality here. So we're going to go on the data, one of the data modules. We're going to go with a simple one. Well, I'm probably going to end up showing you something that I didn't want to, but it doesn't matter. Wait, I can show you one that doesn't have that. I'm sorry, I'm trying to skip some of the complexity of host interrupt right now, because if I were to go for text equality and number equality and character equality, I would have had to talk about how to do JVM interrupt, because that's what I do for that. But I don't need to do any of that for Boolean equality, which is the structure we're gonna see here. Later on, when we talk about interrupt, we're gonna see how to do the other equalities, because I'm using the host platform for those things, but I don't need it for booleans. So here we have an actual structure that implements equality, which is boolean equality. Now this code here looks a little bit weird. Let's say a few things. Here's the syntax for importing modules. It's a little bit different from what we have seen previously. I'm gonna talk about why in a future video where we discuss modules more in detail. But for now, this is just, this e here, this e prefix is, it's an alias for the egg module. So instead of having to write looks control egg semicolon egg, I can just write e. Kind of like, how previously I showed you that you can just write text instead of looks data text when referring to things that come from the text module. It's kind of like that, but instead we're using e as a text. When we talk about modules, we're gonna see that you're gonna understand why it's like that. I'm sorry if the explanation sounds a little bit funky. You're gonna understand it more in future videos. But here's the structure. It's called bool/egg. The name I chose it like that as a convention, but it doesn't have to be like that. It can be anything. It can be anything, really. But I kind of like this convention of type / name of the signature. So this is an egg implementation for boolean, which means that our type for the equals function is gonna be bool, 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 because the bool here comes from the egg being parameterized by boolean, and the bool here is just the equality boolean. It is independent of the type variable. So whereas here we are annotating the names of our members with types, here we are just defining those members. So here I am annotating equals with this type, and here I'm just defining equality. It takes 2 arguments, because remember our function takes 2 elements of a, or of the a type, which is now boolean, and I'm supposed to return another boolean. Now you might notice that in this def expression, this def form, I'm not specifying the type, which I could say this is a function from bool to bool. Very simple, and it will work properly. But it happens to be the case that when you implement structures, every member of the structure gets matched to the type of the signature, so I don't need to write it. I mean, I could, but it's unnecessary. So, the implementation of equality for boolean is pretty simple. If x is true, the result is going to be dependent on whether y is true, because if x is true and y is true, then you're going to get true as the value. It's pretty simple. And if x is false, then y has to be false in order for this to be true. So if x is true, if y is true, you get true as the value, which means true, as equality. And if y is false, then you get false as the value, because you will have gotten true false in the equality, which is of course false. But if this is false, then the node is gonna make it true. So it's gonna be false and false equals true, which is right, because false and false are equal. But if this is false and this is true, it's gonna be like false, true. This is made into false, which means that false and true equals false. I'm sorry if it sounds weird, but it's just that this is the way you can make this pretty simple. You can also make it in a more straightforward way, maybe by simply saying, hey, maybe this is the proper way of doing it for simplifying things. True equals true. False equals true. Anything else, false. Maybe this would have been a more straightforward way of explaining things, but I wanted to be a little bit clever with implementation and a little bit shorter, so I wrote it like this. But they will both implementations will provide the same value. So anyway, we have equality for booleans. So we have seen how to make a signature and how it works, and how to make a structure and how it works. But how do you use it? Well, we have already used structures in our program so far. And right now, what we have done is open the structures. So there is this macro called open. And if you give it a structure and an optional prefix, I mean, you can omit it. And in fact, I'm going to omit it right now because I'm not going to be needing it that much. But if you give it a structure and maybe a prefix, then it's going to open it for you in the global scope, so that it can be used anywhere within your module. Okay, pretty simple. So, you know, when I do this thing here with the when I use this syntax, basically I was saying, hey, here's this prefix, and use it for opening the following structures. And in the case of numbers, you know, you can just do something like this. It's kind of convenient to avoid having to open things explicitly, you know, by yourself. And you know, I could have done something like this, which would have amounted to something like this. But again, you know, if you don't provide any prefix, then it's the same as having this as a prefix. Changes nothing. But you know, if you're going to be using this syntax, you always need to provide a prefix, because the system uses that to figure it out. You know, if it's a string, if it's this text and this is other things, it assumes that the other things are structures. You know, the syntax for when we talk about modules, you're gonna understand all this funky syntax. I'm sorry if it sounds confusing here, but it doesn't matter. Now, open here works for opening things or making them available on a global way. But what happens if you want to do things in a more local way? Well, you can do it. You can actually access everything here without needing to open it globally in some ways, several ways. So one way we're gonna do is, you know, we're gonna be using this, and we're also gonna be using this here. These are the number implementations, and we're gonna be extracting this from here, and text monad. I'm not using the text monad anymore, so we can get rid of that. We're not concatenating anything right now. Now, you know, what is this funky syntax? And first of all, you know, let's make sure that this compiles, because God forbid that I just botched the program. And it compiles. Pretty simple, right? Runs perfectly. What is it? Well, here you have this using macro, and using basically means, you know, within the context of the expression that I am enclosing, open everything so I can use it. It's pretty simple. So it's like opening things without a prefix. Only that it's only going to be seen in here, which is why when I want to use it here too, and I also need to use the using macro instead of just relying on the one from up here. And there is also another way of doing this, but it's a little bit more hardcore, and I won't explain right now how it works because that's gonna be for a future video, but I can do something like this. Notice that here it says open, but it has a backslash, so it's not the same open that we used globally. This open only works on a more local scope, but it does the same thing. And it can even have a prefix too. So let's give it an I, and that means I'm gonna have to use I star for multiplication. And Again, let's make sure this compiles. And it does, no problem. And what is this thing here? Well, backslash open, and using open the structure, make available all of the elements in the structure within enclosing expression. So all the elements in number here are going to be available here, and all of the elements in number over here are also going to be made available here. But that means all of the elements. And number contains a lot of things. It contains functions for addition, subtraction, division, multiplication, comparison, everything you want to do with a number. But what happens when you only want to access one element and one element only? Well, this double column thingy here is perfect for that. So here I am accessing the show function within the int show structure. Pretty simple. And I'm only accessing that. And this actually will be equivalent to saying something like this. Using this, I will splice everything open and have all the things inside show, and then I will just return this thing here. But that will be a little bit wasteful, because why do it when you can just extract one element? Why extract everything when you can just extract one element? So this double column here is great for that. And right now we're only using it to access the element itself, which is the show function. But you're going to use it to apply those functions to other things. So I could say something like, instead of doing this open here, I could say something like, using the InNumber implementation, invoke the multiplication function that is in here for this, and this will all work. This will all work. So this is how you use structures. Pretty simple, pretty easy, and hopefully it will be something that you do very often, because structures are a great way for packaging functionality. And the thing is that they are values like any other, because in fact, just as signatures are implemented in terms of record types or tuple types, structures are implemented as records. So they are values like any other. You can even write functions that take structures and return other structures. You can write functions that combine structures. You can even make structures that take other structures as arguments. It's pretty crazy. And I have a nice example in the maybe module, which implements equality, if I'm not mistaken. And no, I forgot to implement equality. Sorry about that. Let's implement it so we don't forget. So I don't have any. You know what? No prefix. Structures. Def struct. So this will be an implementation of equality for maybes. Like, if you can, let's explain this so you guys understand what's going on. So, what is this? What is going on here? Well, I had to import the equality module to be able to use the equality signature. And basically here I'm saying, hey, for all A types, I'm going to talk later about maybes. Actually, I'm going to talk about maybes in this video. So, let's just say that a maybe is a data structure that represents something that may be absent or may be present. Something that you may have a value or you may not have a value for something. And it's kind of like a container that can contain nothing. It's a little bit funny. We're gonna see later. Point is, if you give me, if I have a way of comparing the equality of things within a maybe, then I have a way to compare maybes, because I just need to figure out whether the maybes contain something and then compare the contents, and that's it. And that's basically what the type means. For all 8 types, if you give me a way to compare equality for the element, I'm gonna give you a way to compare equality for maybes of those elements. And this, since in this type, I take an equality implementation, this is that equality implementation. So the maybe equality structure takes an equality implementation, which is gonna be called a/ig because of the a here, and I have to implement the equals function. So I'm gonna receive 2 elements. I'm gonna call them mx and my because they are maybes. If both are empty, then they are equal. Let's face it, because 2 empty things look pretty much the same. If they contain something in both cases, I just need to compare the things that are contained using the equality that I received. And if one of them contains something but the other one doesn't, which is this third case, then of course I can't compare anything, so I'm just gonna say it's outright false. Simple as that. So this is how you do equality for maybes, and this is how you make structures that depend on other structures. Now you might think this looks kind of funny because, this type implies that there is a function somewhere, and it is. Maybe egg is not really a structure, it's more like a function that generates a structure. And in this particular case, it is a function that if you give me one structure, I'm gonna give you back another structure that is gonna have some added functionality. So if you give me the structure for doing equality over elements, I'm gonna give you the structure for doing equality over maybes of those elements. So that's what it would look like. And finally, I wanted to talk in this video about 3 very important signatures and structures that we're gonna be seeing more of in the following videos, the future videos. One is functors, the other is applicatives, and the other is monads. So first, let's talk about this. Let's talk about this right here in this module, because maybe it's a really good type for talking about these things. So what are these things, and what are even these weird names? Functor, applicative, monad. What the hell are these things? Well, the names come from math, which explains why they're weird. But the concepts are simple. Okay, so check it out. I'm not gonna explain everything as a mathematician would, because when people tend to hear those explanations, they don't understand anything, including myself. When I was, functional programmers tend to have some problems learning those concepts in the beginning, because explanations that people pass around don't tend to be very good. So I'm gonna try to keep things simple and not go too much into the math, to give you something that you guys can understand. So first I'm gonna talk about functors, which are the most basic things. So what is a functor? Well, again, I'm not going to give you the mathematical explanation, but I'm going to give you something that hopefully you will understand. So imagine that you have a wrapper around something, and that wrapper contains something because it wraps it, right? And let's imagine that just as you can operate on the thing while it is wrapped, you would also like to be able to understand the thing inside the wrapper. So you don't want to just work with the wrapper, you want to work with the thing inside the wrapper. But you want to work with it in a way that doesn't escape the wrapper. So it's not like you want to say, like, okay, I put this thing inside the wrapper, then I took it out of the wrapper, and I'm working on that. No, that's not what you want to do. Instead, you want to modify the thing inside the wrapper, but still you want to stay within the wrapper. Now, what the hell is this? It sounds like the most weird thing. It's not mathematical. It's not very mathematical, but it still sounds very, very abstract. What is this whole thing about wrappers? We'll consider something like this. Consider lists, right? Like, remember our function for doing iteration over lists, right? And in our function, we have this list, we have this list, it contains something, and we want to be able to transform the things within the list. But we don't want to get something that is not a list. We still want to get a list. We still want to work within the structure of a list. So we just want to modify the things inside. So in list iterate, I don't change the structure of the list. Like if you give me an empty list, I'm still gonna give you back an empty list. And if you give me a list with n elements, I'm still gonna give you back another list with n elements. So the structure of the list doesn't change, but the elements within it do change. So it's kind of works like that. Sorry, my English gets a little bit funky sometimes. It kind of works like that. You know, I have this structure, I have this procedure that I want to work with, that I want to apply, and I have to apply it to the things within some structure, like our list here. Well, remember how we did equality here? We did something very similar. We're doing equality of elements within a structure, which is the maybe structure. Well, you get something very similar. Well, functors are pretty much that. Functors are basically this signature that basically says, hey, if you have some type that acts as a wrapper, such as maybe here, then if a functor implementation for that type is something that can work with the elements within the structure, but everything stays within the structure. So a function that I apply using the functor on a maybe element modifies the elements inside, but you still get a maybe. So if we had to use maybes instead of list for list iterate, if for getting the count, I will say something like, hey, if you give me a maybe with the word, I'm gonna give you back a maybe with the count of the word. And that's basically what functors do. And just as we had list iterate for doing the kind of stuff with lists, we have this map function for doing that with anything that is a functor. And in this case, maybe is a functor. So basically, if you give me a nothing, I give you a nothing. If you give me a none, I give you a none. Very simple. And it will be like saying, if you give me no word, I'm gonna give you back no count or no size of the word. I cannot give you anything, right? But if you give me some word, then I'm gonna give you some count of the word, which in this case, applying a function f, like in our list iterate, to the element that is wrapped in the maybe, like here, like this thing here. Pretty simple, right? And many things are functors. Lists are functors. In reality, the list iterate function that we wrote tends to get called map, just like this here. It tends to be the name for that in functional programming languages. Now, the map word has some mathematical origins. I'm not going to go too much into that. Let's just say that map is a thing that allows me to apply a function to the contents of a functor. Simple as that. While preserving the structure of the functor. Like, mapping a function to a list, it still gives you back a list, even if the contents get changed. Mapping a function to a maybe, it still gives you back a maybe, even if the contents get changed. So the structure is preserved. So this is the most basic thing, right? Functors. And right now, you might understand some of the power of functors because we saw the list iterate function and how awesome it was. And again, you can have many functors, and the beautiful thing is that different functors have like different superpowers depending on the type as it is implemented. And later on, when we talk more about monads and the kinds of things that you can do with monads, you're gonna see some of the crazy things you can do with functors. But functors are like the basic things, and everything, and a lot of things are built on top of that, including monads. So first, let's talk about applicatives. Applicatives, are kind of like a way of saying, hey, by the way, applicatives are functors, which is implemented by having this functor field within the applicative signature or applicative structure in this particular case that contains a functor. So every applicative contains a functor implementation for its parent functor type. So applicative gives us two things. One thing is, here in this maybe, I can apply here in these functors, in functors I can modify the contents of a structure. But I cannot put something within a structure. Like, if you give me something that is already a maybe, I can work on that, but I have no way of making something from a regular element into a maybe. I have no way of doing that, which is problematic, because how can I get something that I can use with my functors, right? How can I do it? Well, applicatives give you a way. They have this function called wrap. In something like Haskell, it will be named return, but I prefer to call it wrap because functors wrap over the data, so kind of makes sense. So this function wrap, if you give me some piece of data, I'm gonna wrap it inside the functor. So if you give me an int, in this particular case, I'm gonna give you back a maybe of that int, which is by using this sum tag, this sum constructor for maybes. If you can, if this were a maybe applicative, it will. If you give me an element, I will give you a one element list with that element. So basically, give me a raw piece of data, and I'm gonna wrap it in the functor. And finally, there is this apply function. Basically, it's like, okay, if you give me a function that is inside a functor, and you give me an argument that is also inside a functor, I'm gonna apply the function to the argument, and you're never gonna escape the functor. So just it's a way of saying, hey, I have this function that maybe, well, wrong choice of words. I have this function that could be inside a functor, and this argument that also could be inside a functor, and I want to work with them without having to unwrap them manually, because maybe I can't, and I just want to work on them and get the results, and maybe it's going to be successful or maybe not. Well, apply is great for that. Apply allows you to work with functions and arguments that are inside functors without needing to escape the functors. Okay? And finally, we have monads. And monads are really, really, really important. Really, really, really important. And I'm not going to hope that you guys are going to understand how this works right now. And I'm going to expect you guys to understand it now. Not because I think you guys are dumb or anything like that. I think you guys are really smart and really awesome. But monads kind of take a little while to get used to them. So if you don't understand anything, heck, even if you don't understand anything about functors right now, it's okay. It's gonna get easier with time, especially since we're gonna be using them a lot in the other videos. So you're gonna get more used to them. So basically, monad, it's also an applicative, which is why it has this applicative field, and it adds an extra operation called join. And basically, join works this way. It's gonna be weird. It works this way. So let's say that I have a monad type called m, right, and some component type called a, like the component that is wrapped by the functor, because monads are functors. Well, join basically does something like this. Type of join is, if you give me an m of a, I'm gonna give you an m of a. So basically, it fuses or collapses the two layers of the functor or monad structure into one. And that's what it does. Now you might think to yourself, what? Is that supposed to be useful in some way? What the hell is that? What is the point? But the thing is this. This is why this is such an important operation, especially when combined with the map function from functors. Functors, we have already seen that that maybe allows you to maybe have a value or maybe not. Some you have a value, none you have no value. Lists are also functors, right? So you can have no value, which is the empty list, or you can have multiple values, which are the const values. And you can have many other kinds of functors with different powers. But the thing is that consider that maybe gives us values that may or may not be, that may be absent or may be present. Lists gives us multiple values. We can have functors that add other pieces of functionality. So you can see functors as data structures that give you special superpowers for your data. Now, the thing about the join operation is that what join does is that allows you to combine sequences of those superpowers. And basically, what it does is that, with map you can work with your data within the context of a particular superpower. In the case of maybe the superpower of maybe failing or maybe succeeding, and with the join of monads I can combine those things so that I can do multiple computations that all share those superpowers, but I can combine them into one result in the end. And that combination can be done in a very simple way using something that we have seen so far and not explained, which is the do macro. Now, this video is already pretty long, so I'm gonna end it now. I'm not gonna talk too much about this, but do not despair, because for tomorrow we're gonna talk about macros in Lux. And the thing about macros in Lux is that macros work with monads. So tomorrow we're gonna see how the do macro works, what does it do, into what does the sugar, so you can understand the role that functors and monads play in day-to-day Lux programming, and you will understand, why monads are such an amazing tool, even if they look kind of funky. And hopefully, by seeing how everything works in practice, it will become clear to you how everything works, and you won't feel so weirded out by the abstract elements that I have discussed. So for now, this is a video. See you tomorrow.